Hello and welcome to the GCSE Science Tutor. Today we're looking at Lesson 6, History of the Atom. Now before we look at the history of the atom, let's recap electronic structure from last lesson. Pause the video now and have a go at the 3 questions on the screen. And I'll go through the answers in a few moments. So question 1. An atom has the following electronic configuration: 2, 8, 3. Have a go at drawing it. So we can call this element X, as we don't know the symbol. We draw the first shell as a ring, and we can draw the first 2 electrons in the shell. 1, 2. Second ring holds a maximum of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then we need to put the final 3 electrons in the third shell. 1, 2, 3. Question 2. What group will this atom be found in? Explain your answer. The group is the same as the column of the periodic table, and we can tell this by looking at the number of electrons in the outer shell. 1, 2, 3 electrons in the outer shell, so it will be in group 3. And we can write our answer something like this. Group 3, because there are 3 electrons in the outer shell. Question 3. What period will this atom be found in? Again, explain your answer or give reasons for your answer. Well, we can see that there are 1, 2, 3 shells in this atom. 1, 2, 3. So therefore, it will also be in period 3. And again, it's asking us to explain, so we need to give reasons for our answer. And using the word because is really helpful. Period 3, because there are 3 shells. Now, the atom hasn't always looked like what we can see it today. Through different technological advancements, we have discovered different aspects about the atom. So let's have a look at how the atom has changed over time. Here is a task. Draw a timeline with 6 points along it, read the 6 statements below, and try to draw the model from the description. Don't worry about getting it wrong, that's part of the fun. Pause the lesson now, and I will show you my models in the next slide. So the very first atom was proposed by Dalton, which was just a round sphere. The second atom was proposed by J.J. Thomson, who came up with the plum pudding model. He described it as a ball of positive charge with embedded electrons. And embedded is a good word to describe within. It's important we don't discuss protons at this stage because protons had not yet been discovered. The next key model was Rutherford's nuclear model. He proposed that the centre of the atom was in fact a positive charge. Again, these were not protons, but just simply a positive charge in the centre. And called this a nucleus. The next key model was proposed by Bohr. He proposed that electrons were not randomly distributed across the atom, but in fixed positions called shells. The next key atom was that proposed by Chadwick, and his key discovery was the neutron. And finally, in our most recent modern-day proposal of the atom, we can see protons and neutrons and electrons. It would be a good idea to learn these key models and the scientists that discovered the aspects of them. Now that you've drawn the models of the atoms, you could get creative and get out the Play-Doh and have a go at creating some 3D models like the ones shown in these images. It all helps with our memory and remembering the key parts of the model. So here is a practice exam style question. Your task is to compare the plum pudding model and the atomic model, which is also the present day model of the atom. In an exam, this could be worth up to 4 marks, and so it's important that you make at least 4 comparative statements. An exam tip would be, when asked to compare something, it is completely acceptable to use a table, and also advised, because it ensures that you are mentioning both kinds of model. For example, you could draw up something like this: the plum pudding model on the left, the atomic model on the right, and making sure that you mention both models in your comparative statements. Pause the video now and see if you can come up with any other differences or similarities between the plum pudding and atomic model. So here are some of the things that you could have mentioned. Pause the video now and jot them down and add them to your own table. Throughout history, there have been various technological advancements and experiments that have been carried out in order to develop our understanding of the model. A key one was the alpha scattering experiment, which allowed us to disprove Thomson's plum pudding model and accept Rutherford's nuclear model. So what happened in the alpha scattering experiment? Alpha particles were emitted from a radioactive source. Alpha particles are positively charged particles. They were bombarded towards a sheet of gold foil consisting of essentially gold atoms. It was expected that the alpha particles would pass straight through the gold foil and get detected at the back of the detector like this. However, some were unexpectedly detected on the side of the detector. So why is this? Well, most went straight through since atoms are mainly empty space. However, the densely charged positive nucleus deflected some of the alpha particles to the side of the detector. We can see that in these diagrams here too. The Thomson model on the left shows the alpha particles passing straight through the atom because there's nothing dense or positive enough to deflect them away. On the right, we can see the Rutherford model, which has a dense positive nucleus, which is dense and positive enough to deflect the positive alpha particles to the side of the detector. Through the observations made from the alpha scattering experiment, many conclusions could be drawn. Your task is to link the observation made in the experiment to the conclusions that were made from it. Pause the video now and have a go, and I'll go through the answers in a moment. The first observation was that most alpha particles could pass straight through the gold foil atoms and hitting the back of the detector. That meant that most of the atom had to be empty space. The second observation was that some alpha particles are deflected through large angles, hitting the detector on the sides. This must have meant that the nucleus is positively charged in order to deflect away the positive alpha particles. Also, very small numbers of alpha particles deflected straight back towards the alpha particle emitter. That must have meant that the nucleus was also very small, because such a few number of alpha particles were deflected. The next lesson in this unit, we're going to look at Lesson 7, the development of the periodic table. Thank you for listening to the GCSE Science Tutor. Please remember to like and subscribe to get further updates on lessons and tutorials.